Alright guys, so in this video I wanted to talk about combinations. So what are combinations? Well, combinations relate to permutations, so I'm going to start with a permutations example before really diving into what permutations are, what combinations are. So let's go with a permutations example right now. Let's say we have three numbers, okay, 1, 2, and 3, and we want to see how many different ways we can take out two of those numbers. So I'll draw two slots. We're going to take out two of these numbers, how many permutations there are for taking out two of these numbers and then reordering them, right? So for example, we can have 2 and 3, we can have 3 and 2, so on, right? And if we wanted to calculate the actual number of permutations, all we would have to do, if you remember from last video, is say 3 factorial, because there are 3 numbers in our initial group right here, and we'd have to divide it by 3 minus 2 factorial, or in other words, 1 factorial. If this doesn't make sense to you, I suggest you go back to the permutations video. But anyways, this is equal to 6. So there are going to be 6 different ways we can take out two numbers from this group of 3 elements and reorder them. Okay. So we have, I'll write them all out. You'll see why in a second. So we have 2, 3, 3, 2. Actually, I'll start over. You can have 1 and 2, 2 and 1, 1 and 3, 2 and 3, 3 and 1, or 3 and 2. So these are all of our different permutations. 1, 2, 3, 4, 5, 6. Okay. So, what exactly how many different ways how does this relate to combinations, right? Well, we have 6 permutations here, right? Six permutations. And how does this relate to combinations? Well, combinations are sort of like permutations, except they don't take into account the order of elements. So in this case, we have numbers as elements, right? So, for example, this 1 right here would be considered an element. This 2 right here would also be considered an element. All of these numbers here are considered elements. And combinations are sort of like permutations, except they don't take into account the order. So for example, these 2 permutations, 1 and 2 and 2 and 1, they're considered different permutations because they're in different orders. But they are both the same combination. So 1 and 2 and 2 and 1 would be considered one combination because they include the same numbers. So combinations are sort of like saying how many different sets of elements can we get from taking out a number of elements from this group, right? So 1 and 2 would be considered one set that we can get, okay? Or 2 and 3 would be considered a different set. But if we were to take 2 and 1, that would be considered the same set as this 1 and 2 over here, okay? All right. So those are what combinations are. Now let's talk about how we can calculate combinations. Well, it turns out we can actually get the number of combinations by dividing the number of permutations by x factorial, where x is the number of positions. So in our last example, when we had 1, 2, and 3, and we were taking out two different numbers from that group, we had two different positions because we were taking out two different numbers. So this x here would be how many different numbers we're taking out. And that will equal combinations. The number of combinations. Okay. So why does this work? Well, as I was saying in the just before in the last example, I'll just write out these permutations again. Each of these combinations can be represented in some number of ways. So for example, this combination 1, 2 can be represented as 1, 2 or 2, 1. But it's the same combination. Over here, there's another combination, and that can be represented in two ways. So this combination 1, 3 can be represented as 1, 3 or 3, 1. The same goes for this combination. So all of these combinations have redundant sets. And in this case, it's two. In this case, there are two different ways to represent each combination. And that produces one redundant set for each combination. So in order to get combinations from permutations, we really should just have to get rid of these redundant sets, right? And once we get rid of these redundant sets, we have the number of combinations, right? But how do we figure out how to discount these redundant sets so that we can just get the number of combinations, not the number of permutations? Well, we're starting with the number of permutations here, right? This is the number of permutations, and we want to get combinations. How are we going to get rid of, or how are we going to discount all of these redundant sets? Well, we can divide it by the number of different ways each combination can be reordered. So for example, this combination can be reordered in two different ways. So can this one, so can this one. So all of these combinations can be reordered in the same number of ways. So all we have to do is we have to divide the number of permutations by the number of ways we can reorder each combination. And in this case, it's 2. But in other cases, where it's a little bit more complicated, we won't be able to write it all out and then just look at it. We actually need a way to calculate the number of ways each combination can be reordered. So we can actually just take the number of positions factorial. And that equals the number of ways to reorder each combination. So permutations divided by the number of ways to reorder each combination is equal to permutations divided by positions factorial. Or we're just using the variable x. So why is this x factorial over here equal to the number of ways we can reorder each combination? Well, we can take any number of elements, okay, and find out how they can be reordered. So I'll do 5 elements in this case, but it can be for any number. For any number of elements, it turns out that the number of ways this number of elements can be reordered is the number of positions factorial, right? So that's what we're proving right now, right? In other words, x factorial. And we're proving that right now. So let's just say that our elements are A, B, C, D, and D, the first 5 letters of the alphabet. These are our elements, and we want to find out how many different ways we can reorder this. So in this case, the number of different ways to reorder these 5 elements would be 5 factorial, right? Right? And that's the same thing as 5 times 4 times 3 times 2 times 1. So why is it 5 factorial, right? Why does that make sense? Well, let's imagine a tree, which we've done. We did 2 videos ago, I believe. Let's imagine pathways. So our first position can hold 5 different letters, okay? So our first position can hold 5 different letters. It can hold A, B, C, D, or E. Okay. Then after that, each position can only hold 4 letters. Or the second position can only hold four letters, right? Because it can't equal. So, for example, if this first position contained the letter A, the second position could not contain the letter A, right? So for each of these paths, sort of, and we've imagined this before. If this doesn't make sense to you, I'm sort of just bringing this from another video. Hopefully you remember this. If you don't, I encourage you to go back to the other video. But anyways, we're saying that we have 4 different paths after the first few. So this first slot can be A, B, C, D, or E. And then after that, it can be only 4 different letters. So as I was saying, if this first position contained the letter A, the second position could not contain the letter A. So at first we have 5 different ways of picking the first position. And then we have 4 different ways of picking the second position, right? Because it can't be the first letter. And then 3, because it can't be the first 2 letters. And then 2, and then 1. So it turns out we actually have 5 times 4 times 3 times 2 times 1. And by the way, if this is really confusing, I suggest you go back to the other video, because I just sort of brought in this method, but you should be familiar with it if you watched the past 2 videos. Yeah. But anyways, we would multiply these numbers together, because we have 5 different ways for picking the first position, 4 different ways for picking the second position, 3 different ways for picking the third position, 2 different ways for picking the second last position, and only 1 way to pick the last position. And we multiply those together to get the number of different ways we can reorder it. So that is why the number of positions factorial equals the number of ways to reorder each combination. That pretty much concludes this video. Thank you.